The idea of the driverless cars has been around for almost 100 years, but was not created until recently. Google released its first driverless car in 2010, with the intent to release them for commercial use by 2020. Driverless cars would create a much safer and environmentally friendly infrastructure, as they could be programmed to deter accidents, save lives, and reduce traffic, and drive as efficiently as possible, which will reduce emissions. Challenges arise when programming a driverless car braking and accelerating mechanisms. These should be optimized to control velocity efficiently to improve the lives of users. The team's goals is to control the speed of the driverless car by taking input from current position and current speed. The output would be the desired velocity based on these inputs. This will be accomplished by creating a mechanical system with dampers, forces, positions, and masses for both a flat and inclined road. This mechanical system will be converted into an impedance circuit to determine the electrical components that will need to be involved. The mechanical system, impedance circuit, and corresponding feedback loop diagram seen here will be used to model the driverless car's acceleration and deceleration to obtain a desired speed, where m is the mass of the car, approximately 1900 kilograms, and b the drag coefficient of air, approximately 1.05.
The three parameters that we wanted to achieve were rise time, percent overshoot, and steady state error. The desired rise time was less than 3 seconds, so that the car would reach 90% of its goal speed in a short amount of time, but not so short that it accelerates too quickly. The desired percent overshoot was less than 2%, so that if the desired speed was 65 miles per hour, the car wouldn't accelerate past that speed. We also wanted steady state error to be 0%, so that if the car was set to 70 miles per hour, the car would go to 70 miles per hour and not settle at a speed less than that. Settling time was determined not very important in our system because once the car reaches 90% of the desired speed, the last 10% can be achieved slowly without any harm to the system or the user. As seen from the calculated Routh-Horowitz, the leftmost column is all positive and will be stable.
After some research on cars, it was decided to base our driverless car system off a mass of 2,500 kilograms for an average size vehicle and a damping coefficient of 1.5 newton seconds per meter. The result is a final transfer function of 1 over 2500s plus 1.5. This is the root locus from our transfer function. It is obvious that since the pole is in the shaded region, it does not meet the requirements for our system. To fix the failed root locus, we add our parameters that were calculated earlier for a rise time below 2 seconds, a percent overshoot less than 2%, and have a steady state error of 0. For further remedy, we add a real left-hand plane 0 and moved it until it was in the correct region. Since we are using a PID controller, this caused issues with having a gain margin of infinity and a non-existent phase margin. So we added another real left-hand plane 0 and moved the poles and zeros around until they gave us an acceptable phase and gain margin. The phase and gain margin came out to be 81.9 degrees and infinity respectively.
With MATLAB's SIZO tool, the specifications of our closed-loop system were determined to be a rise time of 1.79 seconds, a percent overshoot of 1.71%, and a steady state error of 0%. These specs all meet the goals we had for our system.
The SIZO tool also generated a Bode plot that we used to further analyze our system. Since our phase plot does not cross 180 degrees, our system has an infinite gain margin. Since the magnitude plot crosses at 0 decibels, we get a phase margin of 81.9 degrees at a crossover frequency of 1.03 radians per second.
From the Bode plot previously shown, we see a phase margin of 81.9 degrees. From it, we can determine that our system has an allowable time delay of 1.387 seconds, meaning it can handle an input signal delay of 1.387 seconds before becoming unstable. This delay could be better, but it is okay considering the processing speeds of computers in an autonomous car would be well under 1 second. In our Simulink block diagram, we added a time delay block to verify our system. Using data from our Bode plot, we generated a Nyquist plot that helps prove our system is closed-loop stable. Our p equals 0 because our poles are in the right half plane only, and our n equals 0 because our plot doesn't circle -1. Therefore, z is 0, and the system is closed-loop stable.
Overall, all of our driverless car system requirements for controlling velocity of the car will be met with the plant. We will achieve a rise time of approximately 1.79 seconds, a percent overshoot of 1.71, and a steady state error of approximately 0%. Our system will be safe, stable, and efficient.